Hello everyone, I'm Priya from BSc Chemistry Honors Final Year. Today I am going to present a video for visually impaired students. The name of unit is Hard and Soft Acids and Bases. This book is from Pardeep's edition. The terms acids and bases are routinely used in our daily life. Chemists have been classifying substances as acids and bases since long time. Liovicia noticed that the common element in all acids was oxygen. The word oxygen in Greek means acid former. However, Humphrey Davy showed later that all acids contain hydrogen. It was in 1884 Arrhenius developed the theory of acids and bases known today popularly as Arrhenius theory of acids and bases. According to Arrhenius, an acid is a substance which gives hydrogen ions H plus in aqueous solution, and a base is a substance which gives hydroxyl ions means OH negative ions in aqueous solution. The strength of an acid or a base depends upon its capacity to provide H plus and OH negative ions respectively. The process of neutralization of an acid by a base can be represented by the reaction H plus plus OH negative make form H2O. In 1923, J. N. Bronsted and T. M. Lowry independently proposed a new acid-base theory. According to their theory, an acid is a proton donor whereas a base is a proton acceptor. The acid-base reaction is regarded as a proton transfer reaction. In 1923, G. N. Lewis gave another general definition of acid-base behavior in terms of electron pair donation and acceptance. However, their theory got the recognition only in 1938. According to Lewis, an acid is a substance which can accept a pair of electrons, while a base is a substance which can donate a pair of electrons. In other words, an acid is an electron pair acceptor while a base is an electron pair donor. The earlier definitions of acid and bases were solely based upon the observable properties such as taste, ability to dissolve substances insoluble in water, and their effect on vegetable dyes. The term acid was applied to substances that have a sharp or sour taste, turn blue litmus red, react with certain metals to liberate hydrogen gas, and have the ability to dissolve substances insoluble in water. On the other hand, the term base was applied to substances that have a bitter taste, soapy feel, turns red litmus blue. However, tasting and feeling chemicals are dangerous methods of determining whether the substance is an acid or a base. You should never ever taste or touch solutions of chemistry in laboratory. There are, however, other methods of recognizing acid and bases. For example, acid and bases change the color of certain dyes. On the most common indicators is a vegetable dye obtained from lichen known as litmus. Aqueous solutions of acid turns the litmus red, whereas aqueous solution of bases turn it blue. Thus, any substances which has an unshared pair of electrons can act as a Lewis base, whereas a substance which has an empty orbital to accommodate a pair of electrons act as a Lewis acid. In other words, substances capable of donating a pair of electrons are regarded as Lewis bases, and substances capable of accepting a pair of electrons are regarded as Lewis acids. Acid base or neutralization reactions may thus be regarded as donor acceptor reactions or coordinate covalent bond formation reactions. The classical example of a Lewis acid base reaction is that of between boron trifluoride and ammonia. Using electron dot diagram, we can see that boron trifluoride is the Lewis acid and ammonia is the Lewis base. This is a reaction we can see NH3 plus BF3 forms NH3 BF3 donor acceptor or coordinate bond formation reaction. Levi's concept of acids and bases is very commonly used because of its simplicity and the ease with which the formation of coordination compounds can be explained. In brief, all the usual ligands can be regarded as Levi's bases, whereas all the metal ions can be regarded as Levi's acids. The degree of affinity of a metal ion for ligands can be termed as Levi's acidity, and the tendency of the ligand to combine with the metal ion can be regarded as Levi's basicity. Hard and soft acids and bases. An acid base reaction, according to Levi's concept, involves the reaction between a donor A and acceptor B as to form a complex as given below. The formation of the stable complex between the donor A and the acceptor B depends upon the nature of the species A and B involved. It has been known since long that certain ligands form more stable complexes with metal ions such as Ag+, Ag2+, Pd2+, and Pd2+. On the other hand, certain ligands form stable complexes with metal ions such as Ai3+, cobalt 3+, platinum 4+. Based upon the perfectional bonding, the acid and bases have been classified into two groups, class A and class B, according to their preference. Class A metal ions include alkali metals, alkaline earth metals, and more highly charged ions. For example, titanium 4+, chromium 3+, aluminium 3+, Fe3+, cobalt 3+, etc. Hydrogen ion H+. Class B metal ions include heavier transition metals of second and third transition series, for example, cadmium 2+, mercury 2+. Heavier transition metals in lower oxidation state like Ag+, Hg2 2+, Cu+. Low valent metal ions such as zero valent metals in metal carbonyls. Depending upon the type of metal ions, ligands can also be classified as class A or class B depending upon their preference. Class A ligands include molecules or ions with donor atoms nitrogen, oxygen, fluorine, chlorine. It is important to note that class A ligands prefer to form strong complexes with class A metals. Now, class B ligands include molecules or ions with donor atoms phosphorus, arsenic, silicon, iodine, etc. Class B ligands preferred to form complexes with class B metal ions. It was in 1963 Pearson coined the terms hard and soft acids and bases for class A and class B metal ions and ligands respectively. Accordingly, class A metal ions are referred to hard acids while class B metal ions are called soft acids. Similarly, class A ligands are named as hard bases whereas class B ligands are termed as soft bases. In summary, according to Pearson, class A acids are hard acids like H+, lithium+, sodium+, beryllium 2+. Class B acids are soft acids like Ag+, palladium 2+. Class A bases are hard bases H2, NH3. Class B bases are soft bases R3P, R3AS. Now, classification of acids and bases as hard and soft. Pearson observed that it is possible to correlate acid-base interactions on the basis of hard and soft acids and bases. He observed that type A metal ions acids were small, compact, and not very polarizable, and these preferred ligands that were also small and less polarizable. He called these acids and bases as hard. On the other hand, the type B metal ions and the ligands they prefer appear to be larger in size and more polarizable. He described these acids and bases as soft. Pearson generalized the acid base relationship and expressed that hard acids prefer hard bases and soft acids prefer soft bases. Classification of acids. A general classification of some common hard and soft acids along with some borderline cases is given in table 4.1. So we can see that these are hard acids like hydrogen plus, aluminum 3 plus, chromium 3 plus, Mg2 plus, and these are soft acids like platinum 2 plus, cadmium 2 plus, BH3, titanium 3 plus, CH2 carbenes, and borderline acids are Fe2 plus, CO2 plus, Sb3 plus, Bi3 plus, SO2, RH3 plus. An inspection of table 4.1 reveals that hard acids usually have the following characteristics. Hard acids are cations of smaller size. Hard acids are cations of higher oxidation states. Hard acids are molecules or cations with lesser number of valence electrons. Hard acids hold the valence electrons tightly and consequently are not easily polarizable. In summary, hard acids bind strongly to a proton. Hard acids are small sized, compact, and are not easily polarized. A close look at table 4.1 also reveals that soft acid possess the following characteristics. Soft acids are cations of the large size or heavier elements. Soft acids are cations of lower charge. Soft acids are molecules ions with large number of valence electrons. Soft acids do not hold the valence electrons tightly and are therefore easily polarizable. In summary, soft acids are large sized and easily polarizable ions or molecules that bind strongly to highly polarizable ion or molecule. It is important to note that there is no sharp division between hard and soft acids. There are a number of Lewis acids that are neither too hard nor too soft acids. Such types of acids that are neither hard nor soft are called borderline acids, which are shown on the extreme right of table 4.1. Borderline acids have properties which are intermediate between that of a hard acid and a hard base. In case of borderline acids, the properties such size, oxidation states and polarizability of the cation or molecule are neither too low nor too high. On the other hand, soft acids will show the opposite trend and the following order of preference for binding the donor atoms within a group is observed. The above trend can be pictorially represented as complexes of type A metal, ligands, complexes of type B metal, strongest, weakest, or weakest to strongest. Now, classification of bases. A general classification of some commonly used ligands into hard and soft bases along with the borderline bases is presented in table 4.2. A glance at the table 4.2 reveals some of the important characteristics of hard bases. Hard bases bind strongly to the proton. Hard bases contain donor atoms of high electronegativity. The donor atoms in hard bases possess low polarizability. The hard bases are not easily oxidized. Hard bases contain empty orbitals of high energy. In summary, hard bases bind strongly to a proton. The donor atom in case of hard bases is of high electronegativity and of low polarizability. If further inspection of table 4.2 reveals that the following features are observed in case of soft bases. Soft bases contain donor atoms of low electronegativity. Soft bases contain donor atoms of high polarizability. Soft bases get easily oxidized. Soft bases are associated with empty low-lying energy orbitals. In brief, soft bases contain less electronegative nonmetals. The donor atoms in such bases possess donor atoms that are easily polarized. Just as there are borderline acids, there are borderline bases also. The properties of borderline bases are in between those of the soft and hard bases. It is important to note that the categories are not rigidly divided. For example, the halide ions form a series from the very hard fluoride ion through the hard borderline chloride ion to the borderline bromide ion and the soft iodide ion. The soft acids, also known as class B metal ions, are the group of metal ions that are in the lower right position of the metallic elements as shown in figure 4.1. This is the figure 4.1. Pearson's HSAB principle. Pearson proposed a simple rule for predicating the stability of coordination compounds formed between acids and bases. This rule is quite often named as HSAB principle. According to Pearson's HSAB principle, hard acids prefer to bond with hard bases while soft acids prefer to bond with soft bases. It is important to note that hardness and softness of acids and bases refer only to hard and soft interactions. It is by no means related to the strength of acids and bases. For example, both fluorine negative and OH negative ions are hard bases, but the basic strength of OH negative ion is approximate 10 to the power 13 times of fluorine ion. In other words, hard acids will show the following order of preference of binding the donor atoms within a group. Applications of HSAB principle. Pearson's principle of HSAB has a number of applications in inorganic chemistry. Some of these are discussed below. First, stability of the complexes. We have already noted that hardness and softness of acid and bases are related only to the hard and soft interactions. Hardness and softness of acids and bases has nothing to do with the inherent acidic or basic strength of the acids and bases. For example, both OH negative and F negative ions are hard bases. Although OH negative ion is for stronger a base than F negative ion. In fact, OH negative ion is 10 to the power 13 times more stronger a base than F negative ion. However, in HSAB principle, both OH negative and F negative ions are at par with each other. Pearson in 1963 explained the relative stability of coordination complexes on the basis of HSAB principle. Let us consider a general reaction between a Lewis acid and a Lewis base. A Lewis acid plus B Lewis base make a complex AB. The complex AB will be the most stable if A and B are either both hard or both soft. The complex AB will be least stable if A is hard and B is soft, or A is soft or B is hard. For example, a complex between a soft acid Ag plus and soft base I negative ion is quite stable in contrast to the one between a soft acid Ag plus and a hard base F negative. Ag प्लस एंड आई नेगेटिव के बीच जो हमारा अट्रैक्शन होगा वो सॉफ्ट इंट्रैक्शन होगा, और Ag प्लस और F नेगेटिव के बीच जो होगा वो हमारा सॉफ्ट हार्ड इंट्रैक्शन होगा. सिमिलरली द रिएक्शन बिटवीन Li and iodine and CSF resulting in the formation of LiF and CSI constitute an interesting example suggesting the professional stability of soft and hard combinations. Some of the other important reactions suggesting the stability of the soft and hard interactions are given below. The rule of thumb in determining the stability of the complex is the perfectional formation of hard and soft interactions. Second, classification of acids and bases. The acids and bases can be classified as hard or soft depending upon their preference for hard and soft reactants. Let us consider the following reaction: BH plus CH3Hg plus CH3HgB plus H plus. We already know that H plus is a hard acid whereas CH3Hg plus is a soft acid. If B happens to be a hard base like NH3, the reaction on the left hand side will be preferred. Consequently, ammonium can be written as NH4 plus hard NH3 hard base plus H hard acid, which means the formation of NH4 plus is preferred because of hard acid and a hard base. On the other hand, if B is a soft base like R2S, the right hand side reaction will be favored as shown. R2SH plus CH3Hg plus makes CH3Hg dot Sr2 plus H plus. Conceptually, CH3Hg.Sr2 can be written as CH3HgSr2 plus soft CH3Hg plus soft Sr2 soft base, which means the formation of CH3HgSr2 is preferred because of soft acid and a soft base. Similarly, an acid A can be classified as hard or soft depending upon the direction of equilibrium. We know F negative is a hard base and SCN is a soft base. If A is a soft acid like Ag plus ion, then the above reaction in the forward direction is favored. Conceptually, AgSCN is formed through soft-soft interaction. Hence, according to HSAB theory, the reaction is preferred in the forward direction. On the other hand, if A happens to be a hard acid like Na plus ion, then the forward reaction is not favored, rather the backward direction is preferred. Conceptually, NaF is formed through hard interactions. Thus, according to HSAB theory, the reaction is preferred in the backward direction. OH negative is much stronger base than SO32 negative and hence cannot be displaced by weaker base SO32 negative. This reaction, however, is favored by HSAB principle. CH3CdOH soft interactions plus SO32 negative soft CH3CdSO3 negative soft attractions plus OH negative hard attractions. It is important to conclude at this stage that Lewis acid Lewis base reactions are governed by two independent principles: strength of the acid or base, second softness and hardness of acid and base. The definition of hardness primarily uses the idea of polarizability, which states that a less polarizable species is hard and a more easily polarized is soft. For ions of similar charges, the ratio of charge to radius should be used to assess the relative polarizability or relative hardness or softness. However, HSAB principle does not take into consideration the quantitative idea of relative hardness or softness of the species. In summary, the major limitations of HSAB principle are: HSAB principle is too general and without any qualitative scale of measurement. HSAB principle does not take into consideration the acidic or basic character of the compound. HSAB principle fails to explain the feasibility of the reaction in spite of soft interactions. It is probably the greater acidity of proton H plus relative to CH3 plus G cation that is responsible for the unfavorable reaction. Limitations of HSAB principle. The hardness and softness of an acid or a base is primarily related to stability of the hard and soft interactions. It has no concern with the acidity or basicity of the acid and base. For example, OH negative and F negative are well known hard bases. However, the basicity of a hydroxide ion OH negative is very large as compared to the fluoride ion. In fact, the basicity of hydroxide ion is approximate 10 to the power 13 times that of fluoride ion. A strong acid is well known to displace a weak acid. For example, the reaction between a sulfite ion and hydrogen fluoride proceeds in the forward direction. It means that the stronger base SO32 negative can easily displace the weaker base F negative ion from the acid hydrogen fluoride. However, the above reaction is not favored according to HSAB principle as detailed below. SO32 negative is a soft base. HF is a hard interaction complex. HSO3 is hard soft and F negative is a hard base, which only favors hard and soft interactions. Similarly, a very strong base OH negative can displace a weak base from a soft acid methyl mercury cation. However, the above reaction is also not favored according to HSAB principle, which only favors hard or soft interactions. In both the above case, it is the inherent strengths of the bases that forces the reactions in the forward direction in spite of less preferred formation of hard-soft pairs in the product. This is true in cases especially when the inherent strengths of bases being compared are significantly different. The order of the basic strengths being OH negative is having 15.7 is greater than SO3 2 negative having 6.8 is greater than fluoride ion having 2.85. In other words, significant different basic strengths forces the reactions 4.1 and 4.2 against the wishes of hard soft interactions. However, when both the strengths of the acids and bases and hardness softness are not significantly different, then HSAB principle works well, resulting in products having hard and soft combinations. For example, CH3HgF plus HSO3 negative gives CH3HgSO3 negative plus HF, and CH3HgOH plus HSO3 negative CH3HgSO3 plus HOH. It is important to mention that the inherent strengths of acid and bases should not be ignored while applying HSAB principle. Symbiosis. The hardness or softness of an acidic or basic center is not an inherent property of an atom but depends upon the substituents. Thus, ammonia is a hard base while pyrene is a borderline base. The acidic B3 plus ion is borderline between a hard and a soft acid. Addition of three small sized non polarizable substituents like fluoride ion make it a hard Lewis acid, whereas addition of electron donors and easily polarizable group like hydride ion make it a soft Lewis acid. The difference in the hardness and softness of BF3 and BH3 can be illustrated nicely in the following examples. Jorgensen 1968 observed that hard ligands have a tendency to combine with a metal ion having hard ligands, and soft ligands have a tendency to combine with a metal ion already having soft ligands. He coined a term symbiosis for such interactions. The hard BF3 molecule prefers to combine with hard base fluoride ion to form tetrafluoroborate BF4 negative, whereas soft acid BH3 prefers to combine with soft base H negative ion to give tetrahydroborate BH4 negative ion. An important outcome of symbiosis is that symmetrical substituted compounds are formed in preference to the unsymmetrical substituted compounds. For example, compounds containing mixed substituent interact strongly to yield symmetrical compounds with the same substituent as given below. Similarly, mixed fluorinated methanes react to give symmetrical methanes. In brief, symbiosis may be defined as a tendency of soft ligands to combine with a metal ion already having soft ligands, and the tendency of hard ligands to combine with a metal ion already having hard ligands. Theoretical basis of hardness and softness HSAB principle. A number of theories have been proposed to explain the preference of hard acids towards hard bases and soft acid towards soft bases. First, electrostatic interaction theory. According to this theory, hard acid and hard bases form purely ionic compounds. Therefore, hard interactions are purely ionic or electrostatic. Most of the hard acids such as lithium plus, sodium plus, potassium plus, and hard bases such as O2 negative, F negative, and OH negative, etc., are well known to form ionic compounds. We know that the electrostatic energy of an ion pair is inversely proportional to the interatomic distance. It means the smaller the ions, the smaller will be the internuclear distance, and hence greater will be the electrostatic energy between the ions. As a result, the final compound formed by hard acid and hard base will be highly stable. Second, polarizing power and polarizability. Electrostatic interactions cannot explain the soft interactions because of the bigger size of soft ions. Therefore, the interactions between large sized acids and base must involve covalent character. For example, soft acids such as Ag plus, Hg plus, Cu plus form strong compounds with soft bases like S2 negative, I negative, etc., which have substantial covalent character. Almost all the soft acids have 6 or more d electrons. Soft acids with d10 configurations are excellent soft acids, Hg2 plus. It is these d electrons that have more polarizing power. Secondly, the soft bases like S2 negative and I negative are easily polarizable. Thus, bonding between soft acids and soft bases is largely covalent. Natural occurrence of ores and minerals. The natural occurrence of ores of certain metals can be easily explained on the basis of HSAB principle. Hard acid metal ions such as Mg2 plus, Ca2 plus, aluminium 3 plus, Fe3 plus, chromium 3 plus, etc. frequently occurs as their oxides, fluorides, chlorides, and carbonates. This is primarily due to their preferred hard acid hard base interactions. We know that oxides, halides, and carbonates are all hard bases. These hard acid metal ions cannot occur as sulfides because S2 negative is a soft base and cannot form stable compounds. On the other hand, soft metal ions such as Cu plus, Ag plus, Cd2 plus, Hg2 plus, Pd2 plus, etc. occur invariably in ores as their sulfides due to soft acid soft base interactions that result in the formation of stable compounds. Complex. Interestingly, the borderline acids like CO2 plus, Ni2 plus, Pb2 plus, Zn2 plus can occur both as sulfides as well as their oxides or carbonates as a result of their intermediate character. Catalytic poisoning. All metal atoms are soft acids. Some of the metal, namely V, Cr, nickel, palladium, platinum, are well known catalysts. These metal catalysts have been found to be easily poisoned by soft bases like carbon monoxide, unsaturated hydrocarbons, organophosphines, and organooracines. This poisoning is attributed to the soft acid soft base interactions between the metal atoms and the soft ligands. In fact, these soft ligands are adsorbed strongly on the surface of the metal and block the reactive sites by forming metal complexes. In other words, the metal atoms lose their activity and are said to be poisoned. The soft bases complex with the metals in atomic state will act as poison towards metal catalysts. Electronegativity and hardness, softness. Hardness and softness are related to electronegativity. Species with higher electronegativity values are assigned greater hardness, and those with lower electronegativity values are assigned greater softness. Electronegativity conventionally means the power of an atom in a molecule to attract electrons towards itself. However, in that case, it refers to the power of an individual ion participating in a reaction. For example, lithium atom is known as highly electropositive or lowly electronegative metal, but the cationic species Li plus with very high second ionization potential has a greater tendency to attract electrons towards itself. As a result, lithium plus is considered to be more electronegative and hence is a hard acid. On the other hand, heavier transition metals ions in low oxidation state like Cu plus, Ag plus, Hg plus, Cd plus, etc. have relatively low second ionization potentials and consequently possess low values of electronegativity. As a result, these ions are considered as soft acids. Using the same concept of electronegativity, we can define hard and soft bases. This relationship between hardness and electronegativity can explain several time features as to why trifluoromethyl group is a harder compared to methyl group. Boron trifluoride is harder compared to borane. Ammonia is harder than trimethylamine. Trifluorophosphine PF3 is harder than phosphine. PH3 which in turn is harder than trimethylphosphine. Mulliken Jaffe defined electronegativity as a linear function of the partial charge developed on an atom according as A plus beta del, whereas A alpha is electronegativity of the atom, B is rate of change of electronegativity with charge. The electronegativity value A of the atom is similar to that of Pauling or Eldred Roche, and the parameter B is called charge coefficient. Small hard and non-polarizable atoms have higher values of B, whereas large soft and polarizable atoms have smaller values of B. Parr and Pearson introduced to a new term called absolute hardness for neutral as well as charged species and correlated it with absolute electronegativity. The absolute hardness is defined as one half the difference between the ionization energy and the electron affinity, and neta is equal to 1 minus A upon 2. I is ionization energy, A is electron affinity of the species in question. We know Millikan's definition of electronegativity is delta is equal to 1 plus A upon 2. The hardness of a base B and acid A may be given as base के लिए neta species B plus is equal to 1 by 2 I of B plus minus A of B plus. In order to understand as to why in the equation 4.6 the base B is represented as B plus, whereas in equation 4.7 acid A is represented as such as A, let us consider the interaction of acid A and base B to form the compound AB. In the formation of compound AB, electrons will move from B to A, which is indicated by partial delta plus and del negative charges. Okay, hardness of B refers to a species going from del plus to a charge 1 plus del plus, while hardness of A refers to a species on ionization from del negative to a charge 1 plus del negative. If the shift of charge delta is taken as equal to 0.5, then the charge on B becomes 1 plus 0.5 is equal to 1.5, and on A becomes 1 plus minus 0.5 is equal to 0.5. Thus the charge on B changes from 0.5 to 1.5 with an average half of 0.5 plus 1.5, which is equal to 1, and that on A changes from minus 0.5 to 0.5 with average 1 by 2 of 0.5 minus 0.5, which is equal to 0. That justifies the reason why species B is shown as B plus and A as neutral in equation 4.6 and 4.7. This is a table. A close inspection of the tables 4.4 and 4.5 reveal that the absolute hardness values are in good agreement with their non-chemical behavior. Hydrogen is the only exception which is different in all the three tables. It is advisable to consider it as a special case. With the exception of H negative, the values of hardness parameters of all other bases are as expected. The hard bases F negative and OH negative have larger values of neta B, while the soft bases SH negative and CH3 negative has smaller values. The hard acids such as Na plus, Mg2 plus, Ai2 plus have large Na values, whereas the soft acids such as Ag plus, Cu plus, Au plus have small neta A values. Borderline metal ions such as Mn2 plus, Fe2 plus, Ni2 plus and Zn2 plus have intermediate values. It is interesting to note that down a column in the periodic table from Mg2 plus to Ba2 plus, there is a steady increase in the softness. Similarly, observation of softness is made in going from Ni2 plus to palladium 2 plus. There is also an expected increase in hardness values with increase in the oxidation state as Fe0, Fe2 plus, Fe3 plus. However, there are certain discrepancies as well. For example, titanium plus and titanium 3 plus. The neta A value of titanium 3 plus suggests it to be harder acid, whereas titanium 3 plus is well known to be chemically softer. However, a comparison of titanium 3 plus with other trivalent ions show the expected soft character. Soft acids are generally transition metals in low oxidation states containing loosely held d electrons. These electrons can be easily donated to ligands. On the other hand, soft bases are pi bond acceptors such as phosphines, CO, R3P, alkenes and alkynes. In soft acid-base interactions, pi bonding is very important. Sigma bond formation due to donation of electrons from the base to the metal is reinforced by pi back donation from the metal to the base. Relation to molecular orbital theory. Molecular orbital theory is a powerful tool for explaining structure and bonding, visible UV spectra, and detailed mechanisms of chemical reactions. The concept of absolute electronegativity and hardness can also be explained using molecular orbital theory. The ionization energy is a measure of the energy of the highest occupied molecular orbital HOMO, whereas the electron affinity is a measure of the energy of the lowest unoccupied molecular orbital LUMO, with change in sign for a given molecule. The hardness and softness depends upon the average gap between the HOMO and LUMO. The combination of soft acid with soft base is analogous to the situation in which LUMO of the Lewis acid has about the same energy as the HOMO of the Lewis base. The combination of orbitals results in greatly reduced energy for the electron pair coming from the base as shown in figure 4.2, thus giving a strong covalent bond. For the hard acid and hard base, there is a greater mismatch of LUMO-HOMO energies, so that there is little energy advantage to be gained from orbital interaction. Thus, covalent bonding will not occur to any significant extent and an ionic attraction will result instead. Thank you.